seminario, dándoles la bienvenida a Alfredo Cano y a sus alumnos en Toluca. Nos da mucho gusto que compartan con nosotros el seminario. Y bueno, les doy la bienvenida a todos ustedes. Es un gusto muy grande poder empezar este semestre con la plática de Franziska. So thank you, Franziska, very much for agreeing to give this talk.
Yeah,
so Franziska is currently a postdoc at Frankfurt University, right?
Right, yeah.
And she's visiting Ángeles at the Facultad de Ciencias. So thank you, Ángeles, for sharing her with us. And thank you for giving this talk. So the title of the talk is on the screen. Por favor, les pedimos silencio en Toluca porque les pedimos silencio en Toluca porque creo que es interferencia. Okay.
So thank you very much for the nice introduction. First of all, I want to cordially thank Mara for the generous invitation to Mexico City. It is the first time for me to be here, and I'm really impressed about the people, about the landscape, about the food. It is a bit different than the Mexican food I tried in Frankfurt. I'm a bit confused, but okay. But it is really great, and also for the great host. And last but not least, of course, also for the opportunity to give a talk in Monika Club's seminar. It is really an honor for me, so thank you very much. So the title of my talk is Bubbling and Non-Bubbling Behavior of Solution for Different Prescribed Curvature Problems. And the outline of the talk you can see here. So first we state the main problem. And since this problem is already answered, we can continue this problem in two different directions. So the first one concerns the prescribed Gauss curvature problem, and the second one is about the Ricci flow. So we will start then with the prescribed Gauss curvature problem. There I will formulate the problem, followed by some necessary and sufficient conditions to solve this problem. And then we turn to the special case when the characteristic of the manifold is negative. There we will see some uniqueness and non-unique result, and we will also have a look at the structure of the solution set. So after this first branch, we go to the other direction in which we can continue this problem. So we switch to the Ricci flow. There I give you a short motivation why originally the Ricci flow was introduced. And I will also show some classical results. And since the bubbling behavior for the Ricci flow is motivated by a bubbling behavior of the harmonic map flow, I would like to give you also a short introduction to the harmonic map flow. So we see there some classical solutions and weak solutions. And they were able to construct a new kind of singularity named reverse bubbling singularity. And thanks to this singularity, they were able to construct a new weak solution which differs from this weak solution and from the classical solution. And then motivated from here, we go back to the Ricci flow, and we also introduce weak solution for the Ricci flow to see if we also get another solution like this one from the reverse bubbling, but as you can see here, we do not get that. We still get this classical solution here for the Ricci flow. So this is the outline. So let's start with the main problem. So a classical problem in differential geometry is to classify Riemannian manifolds. A famous proof is this one of the Millennium problem of Perelman. He was able to classify 3 manifolds. But also in 2 dimensions, it is a very hard and interesting problem for closed manifolds. So in this case, we considered a closed, smooth, connected, oriented Riemannian surface with a smooth Riemannian metric. And now the question is, does there exist a metric G bar which is conformal to this metric? So this means we can express it in this way, such that the curvature of this metric is constant. And if we can do that, this is a very good classification, because then we can say this metric is conformal equivalent to a constant curvature manifold, and we just have to consider these constant curvature manifolds. So, and a positive answer to this question is given by the uniformization theorem. This exactly states, yes, this is true for any smooth initial manifold and initial Riemannian metric. And you can find such a background metric. So the background metric is this G bar. And this background metric has constant curvature and is conformal to this initial metric. So, and since we now have an answer to this question, we can continue this question. First, now we say we are not anymore interested in constant curvature manifolds. We still consider manifolds, Riemannian curvature which are conformal to the initial manifold, but now I give you a function f, and we are looking for a Riemannian metric such that the curvature of this metric equals f. So when you see here would be f equal to this constant k bar. And here it is a general smooth function. So this is the first thing you can consider, but you can also go back to the constant curvature case, but now you are interested in the evolution of the manifold. So let's say you start with a deformed soccer ball, and you want to have at the end a round soccer ball, and you want to see also the deformation between. How does this develop and so on. So this means you consider a family now of metrics, and these metrics should distribute the curvature over the time such that in the best case this flow converges to this constant curvature metric. And in both cases we can consider the solution sets. Here we ask for bubbling behavior, here we ask for reverse bubbling. So this I will explain also a bit later, so this expression. So let's start with the prescribed Gauss curvature problem. So I give you a closed Riemannian surface. Closed means just compact without boundary. So it is something, for instance, like that. This is a closed manifold with genus 2 because we have 2 holes. And on this manifold we have a smooth background metric G bar. And I also give you a smooth function f. And now the question is, first, is there a conformal metric such that the curvature, the Gauss curvature of this Riemannian metric equals f? And if the answer is yes, then the question is this uniformly determined by the curvature, or does there exist several solutions? And then we also want to describe the structure of this solution set we find here. So first of all, by the uniformization theorem, we can always start with such a manifold where this G bar is the background metric. So we have a constant curvature metric, and also without loss of generality, we can normalize the volume to unity. And then we know for conformal metrics, we can express the Gauss curvature of this metric just in terms of the Gauss curvature of this background metric, which is just given by the Gauss equation written here. And therefore, we already have our equation, because the question about existence and uniqueness of the solution set just concerns the solution of this equation here. From here to here, we just replace now this curvature here by f, by this given function f. And now we are looking for solution for this equation here. So first we need some conditions on f to solve this equation. So if we have a look at this equation here, we integrate on both sides with respect to the background metric G bar. So on this side here, we use that the volume element with respect to G can be expressed as e to 2u times the volume element with respect to the background metric. So here we just get this integral here. And when we integrate this with respect to the background metric for the first term, we get 0 just by integrates by parts, and the manifold has no boundary. So this term is 0 when we integrate it. So we just get the integral over this k bar here, which is written here. And then from here to here, we just use that this k bar is a constant, so we can pull it out. And we use that the volume is normalized, so we just get k bar. And from here to here, we use the Gauss-Bonnet theorem, so we can express this with the help of the Euler characteristic. And from here now, we get first necessary conditions, namely when the characteristic is positive, this means that also f must be positive somewhere. And if the characteristic is negative, this means that either f changes sign or f is identically 0. And the last case, when the characteristic is negative, this means that also f must be negative somewhere. And now, surprisingly, so this condition here, that f must be positive somewhere when the characteristic is positive, is also sufficient in the case of the projective plane. So this was a result by Moser. So in the case of the projective plane, the condition that f must be positive somewhere is sufficient and necessary to find a solution for the prescribed curvature problem. And in the general case, when the manifold is the sphere, this is called the Nirenberg problem. This is much harder but they also got further necessary conditions to solve the problem by Kasten and Warner, and also further sufficient conditions by Zhang Yang and Zhang Liu and other authors. But there is just little known about the structure set of these solutions. So now we turn to the case when the characteristic is non-positive. There we get further necessary conditions for the solvability. So we consider again the equation, then we multiply it on both sides with the factor e to the minus 2u, and then we integrate with respect to the background metric. So on this side we just get the integral of f with respect to g bar, and on the other side we get this here, and then we integrate by parts, so we arrive at this integral. And now you can see that this integral is non-positive because this is a non-positive term, and the k bar is also non-positive since the characteristic is non-positive. Here is again the condition from before. Here you can see when this is non-positive also the curvature and the characteristic are non-positive. So, and we have equality here if and only if both of these terms are 0, and this is exactly the case when the characteristic is 0 and when f is identically 0. And indeed, Kasten and Warner could show that these two conditions, so this one is the one from before, and this one here is this written here, are both necessary and sufficient to solve the prescribed Gauss curvature problem in the case when the characteristic is 0. But still, we do nothing know about the structure of the solution set. So in the joint work with Michael Struve and Luca Galimberti, we focused then on the case when the genus of the manifold is greater than 1, so we have at least 2 holes. This means that the characteristic of the manifold is negative, and therefore also the curvature is negative. And in this case, solutions to this equation here can be characterized just as critical points of a corresponding energy, which is the prescribed Gauss curvature energy, and is stated here. So now to find solution for this equation, we just need to find critical points of this energy here. So a first observation is, in the case when the function f is non-positive and not identically 0, then this energy here is strictly convex and coercive. And therefore it means that the function f has a unique critical point, and this is a strict absolute minimizer of the energy. And therefore this means that for our prescribed Gauss curvature problem, we have a unique solution in the case when f is non-positive and not identically 0. So now we see, before we said when the characteristic is negative, then f must be negative somewhere, and here we assume that f is not positive. So this is quite a strong assumption. We are also interested in a sign changing function, and for that we need first a bit a technical result, namely the non-degeneracy of relative minimizer. So here we consider an arbitrary function f. So here we do not say anything about the sign of f, and if we have this f and there is a relative minimizer corresponding to this function f, then this point is a non-degenerate critical point of the energy. So this means the second derivative of the energy of this point is positive. And therefore, if we have a relative minimizer of the energy, we know that this minimizer is also strict. And now with the help of that, we can show the following result. So we use again Aubin's result from the unique solution. When f is non-positive and identically 0, we already know we have a unique solution to that. And then with the help of the implicit function theorem, we can now show that also for certain sign-changing function, the energy admits a critical point, which is a relative minimizer of the energy. So the precise statement is that here. So now we know also for certain sign-changing function, we get a critical point. So we can just consider the following family of functions. So we define f0, which is non-positive, such that the maximum of f is equal to 0. And then we just consider f lambda, which is f0 plus lambda. And so we can just change now this lambda to consider sign-changing function f lambda, and then we can consider how long and how many solutions we get for this f lambda. And from this result here, we know that there exists a lambda star positive, such that for all lambda in this area, the energy admits a strict relative minimizer, and this relative minimizer depends smoothly on lambda. So this means in particular when lambda goes to 0, then this u lambda converges smoothly to u0, where u0 was this unique solution provided by Aubin. So, but a first observation for this sign changing function is that the energy is not bounded from below. This you can see just when you consider a comparison function v, which is non-negative and not identically 0, and this function should be supported in the area where f is strictly positive. And then you consider this energy here for a large S, and you see this term will dominate, so the energy is not bounded from below for a sign changing function. And so this means when we have a sign changing function f, and here a strict relative minimizer for this function, which is like that, and we know that the energy is not bounded from below, this means that there must be a mountain pass geometry. And we expect a further critical point, which is of saddle type. So, and in fact, Ding and Liu could show this result. They could show for our choice f lambda as before, that there exists a lambda star such that for all lambda in this area, the energy has a local minimizer u lambda, and this is this here, and also a third critical point u upper lambda, which is of mountain pass type. So when we have a look at the bifurcation diagram, we see when lambda is negative, we have a unique solution, and when it is positive, we immediately get at least two solutions here. And if lambda is too big, then we do not get any solution anymore, because then f0 plus lambda does not fulfill any more the necessary condition that the integral over this function here is negative. So we see that for lambda small enough, we have two different solutions, u lambda and u upper lambda. They are different, and this small solution u lambda converges smoothly to this unique solution provided by Aubin. And now the question is, what happens to the large solution u upper lambda when lambda goes to 0? So we have seen uniqueness may be lost when f is sign changing immediately. And now the question is, what is the geometric shape of these solutions? So actually, in order to characterize geometrically these solutions, we would like to apply different results from authors who were also dealing with this bubbling analysis, just to show that this u lambda blows up in a round bubble when lambda goes to 0. But we are not allowed to use these results here because f is sign changing, and we do not have this uniform bound on the volume, which is required for that here. But in our joint work with Luca and Michael, we used Michael's monotonicity trick, and thanks to this trick we were able to get refined estimates on the energy and also on the volume, and because of that we were able to describe also the behavior of this large solution when lambda goes to 0. So, and indeed we could show the following result. So we assume that all maximum points of f are non-degenerate, and then we can show that there exist finitely many points, and in these points, indeed, the large solution converges to a round bubble. This is written here. So it blows up in these points here, and outside of these points, we consider now this punctured manifold without these points where the large solution blows up. This solution converges to a function u infinity, and this function induces a complete metric on the punctured manifold with curvature f0. So you have something like that maybe. So you have your finite number of points, and in this point you have the bubbles which blows up, and in these points here, just that to get a complete metric, you have these cusps, and then you can here bubble off this in these points. So for the proof, just an idea of the proof. First, you need to define a mountain pass path from u lambda to v lambda. So we have seen that there exists this lambda star such that for all lambda in this interval, we know that the energy admits the strict relative minimizer, which is depending smoothly on lambda. And since the energy is not bounded from below now, we know that there exists a function in H1 such that the energy of this function is strictly smaller than the energy of this relative minimizer. So here and here. And now we just describe a path from here to here. This we do with the standard min-max, just to find this mountain pass point. And this is given here by this C lambda here. So actually we should start here with U lambda, but since they are very close to each other, we can just start with U0. And now the question is there really a critical point at this level here? So, and for that, first thing is when you consider this here, we see that this function here is monotone, and this means that it is differentiable almost everywhere. And now with this property, since we know that this function here is differentiable almost everywhere, we first start with the points where this map is differentiable. So we take a mu such that mu maps to C mu is differentiable, and we show that there exists a critical point U lambda at level C lambda. And for that, we just consider these limits here, which flow to the right properties. And with the help of that, then we can show that indeed there exists such a point which fulfills the desired properties. So this step 3 is just to show for the differentiable points that we get indeed this saddle type critical point at level C lambda. And now with the help of that, we can go to step 4 and show the analogous result just for points where this map is not differentiable. And for that, we just say, okay, mu is a point where the map is not differentiable. Then we just take a limit of points where it is differentiable, which converges to this mu. And for this, we know the result that there is this critical point at this level. And then we just need to show that this set is relatively compact, and therefore we know there exists a convergent subsequent, and we get also the desired properties for the points where the map is not differentiable. So it remains to show the bubbling analysis. As I mentioned before, these are the results we wanted to apply, but we cannot do that because of the lack of the uniform bound for the volume and the energy. But with our monotonicity trick, we could get better estimates for the energy and the energy and the volume, and thanks to that, then we could go just in isothermal coordinates and take an appropriate rescaling to show that indeed in these points these functions bubble off in this sense here. So this was for the first problem here. And now we switch to the Ricci flow. Again, now we want to consider constant curvature metric, but now we are interested in the evolution of the manifold. So I give you again a closed, smooth, connected, oriented Riemannian surface with a smooth Riemannian metric. And now the question is, does there exist a family of metric with the initial data G0 such that this family converges to a constant curvature metric? And this question was solved actually, or the Ricci flow gives you an answer to this question here. So Hamilton introduced the Ricci flow in 1982. And he wanted to improve a Riemannian metric by means of a heat equation. So the initial motivation was to uniformly distribute the curvature of a manifold over the manifold, similar to the diffusion for the heat equation. So, and here is a short movie. And I think this is one of the first time this movie works, because at other universities never works. So UNAM is quite advanced to other universities. So as you can see here now, it starts to shrink where the curvature is large, and it starts to expand the manifold where the curvature is low. And ideally now the curvature will be uniformly distributed over the manifold, and at the end you should get a manifold with constant curvature.
Did you do that yourself?
No, this was Rubinstein and Sinclair. It is not so easy to do that because, this really paper is really nice, and he provided me. So Rubinstein and Sinclair did this movie. Yeah. So, and you can describe the Ricci flow in 2 dimensions with this equation here. So the small r is just the average of the scalar curvature, which is denoted by capital R. So it is given by this term here. And this front term here, small r times g, is called the normalization term, and this ensures that the volume of the manifold remains constant throughout the whole deformation. So it means at any time t you have the same volume as at the beginning. And when you have a look at this equation here, you see that the change in the metric here is just pointwise a multiple of the metric itself. And this means we stay in the conformal class of this metric. And with this, we can express our solution here just again in terms of a conformal factor times a background metric. So, and this background metric, again, we can choose that they have constant curvature thanks to the uniformization theorem. And also, without loss of generality, again, we can assume that the volume with respect to the background metric equals the volume of the initial metric. And now we can plug in this here and calculate a bit. Then we arrive at this equation here. And the advantage now is that we just have an equation for the conformal factor. So we just solve now this to get this metric here. And from here to here, we just apply the Gauss equation. So from now on, we are just considering this equation. And Hamilton and Cho could show that for smooth initial data, there exists a unique global in time smooth solution for the Ricci flow, which converges exponentially fast to a constant curvature metric. So in the following, we will call this solution here reference solution. And also here we have an energy, namely the Liouville energy. And for classical solutions of the Ricci flow, we can show that the energy is decreasing. And therefore, we also see from here, we see that the Ricci flow is the negative gradient flow of the Liouville energy. And when we integrate this equality here, we get furthermore a uniform bound for the energy. And this property we will also use later to define our admissible weak solutions for the Ricci flow. So in general, the question about global or local existence and uniqueness for weak solution is a natural problem in geometric analysis, as can be seen in several examples from Terence Tao and also Michael Struve, Oliver Schnürer, and so on. And the initial motivation to introduce a weaker solution for the Ricci flow in dimension higher than 2 was because they didn't have a classical long-term solution for general closed manifolds. They could show that when you have an initial manifold with strictly positive Ricci curvature, there exists a long-time solution, but not for general manifolds. Then there just exists a short-time solution. And although we have in 2 dimensions a classical long-time solution, the similarity between the Ricci flow and the harmonic map flow makes it very attractive to also consider weak solution for the Ricci flow. Because for the harmonic map flow, they were able to construct new solutions by introducing weak solutions, and they have a lot of similarities together, and because of that we were also interested maybe to construct new weak solution if we introduce a weak solution for the Ricci flow. But to understand this a bit better, now we switch to the harmonic map flow. So we consider now 2 closed Riemannian manifolds M and N, and for these manifolds we can define for a given smooth function between these manifolds the harmonic map energy, which is just a generalization of the classical Dirichlet energy. Because here in this nabla and in the absolute value, of course, all these metrics are involved, so it is just a generalization of the Dirichlet energy. And now we can say that critical points of this energy are called harmonic maps, and therefore they necessarily satisfy the Euler-Lagrange equation of the energy, which are given by this equation here. So this is the equation. When a function fulfills this, then it is called harmonic. So, and then Ilse and Sampson introduced the harmonic map flow to solve the so-called homotopy problem. The homotopy problem says when I give you an initial smooth function between 2 manifolds, does there exist a function which is harmonic and homotopic to this initial function? And they could answer this question, namely here. So for complete closed-oriented smooth manifolds, they could show that indeed For a smooth initial data, there exists a unique global smooth solution of the harmonic map flow. And this solution converges to harmonic map, which is homotopic to the initial map. But they had to assume that the target manifolds has non-positive sectional curvature. This is really essential. So, and the energy behavior of this solution is also, we can see, so the harmonic map energy is also strictly decreasing for such solution. And in fact, the harmonic map flow is the negative gradient form of the harmonic map energy. So here we see the similarity to the Ricci flow before. The energy was also decreasing for classical solution, and it was also the negative gradient flow of the energy. So as a remark, so short time existence and uniqueness can always be shown for arbitrary closed tangent manifolds. But this curvature bound in the result is really essential to get global existence. Otherwise, you have blow up. And so, in order to consider global solutions, it is necessary that maybe you relax the notion of a solution to get a long-term solution. And they did that in a very natural way. They said that the function u in the Sobolev space is a weak solution of the harmonic map flow if u solves the harmonic map flow equation in the weak sense. And then for this definition, Michael could show, when the dimension of the manifold M is 2, that indeed there exists a global weak solution now, which is smooth away from at most a finite number of singular points. And this solution, we call it Struve solution, is also unique in a restrict class of functions, which is denoted by this property here. So, and the energy behavior now of this weak solution is also that the energy is non-increasing. And when you arrive a singular time, so this Ti is a singular time, you have these downward jumps here. So this is a further property for the energy behavior. So you can imagine, like, when you approach a singular time, then you can observe the energy concentration, and by an appropriate rescaling, you can extract a harmonic two-sphere, which we call a bubble. And Struve abandons this bubble just by taking the weak limit of the flow and restart the flow. And because of that, you lose the energy of this bubble when you achieve a singular time. So you have a decreasing energy, then you have this k times the energy of this bubble you lose, and then again decreasing energy. So, and then Frere could show that it is not necessary, when we go back, just for a second, it is not necessary to assume this condition here to get the Struve solution. He said it is enough to consider weak solution and say the solution should have non-increasing energy. And when you assume this, you immediately get the Struve solution. And so the question is now a bit, what happens when we do not say that the energy has to be non-increasing? Do we get then another solution? And exactly this question asked Topping, and he was then able to construct a new type of singularity for weak solutions. We call it Topping solution. And this Topping solution is different from the Struve solution. This is the exact statement, but the construction is very interesting. So he just said that the construction is that you have a perfectly smooth flow, and this flow can spontaneously develop a singularity. So he described that as an addition of an infinitely concentrated bubble. So the imagination now is you have a perfectly smooth flow, then you add a bubble, and then this bubble distributes itself as time increases. So when you look from the other side, it looks like energy concentration. So, and because of that, he called that reverse bubbling. So, and in singular points, this energy jumps up when reverse bubbling occurs. This is a main fact of this energy.
And this is also in the dimension 2, right?
This here is also dimension 2, yeah. Okay. You can construct several examples. This is just, he just wrote in the paper an explicit example, but you can construct several examples for this thing. But yeah, always in dimension 2 he did that, for the disk and the S2. Exactly. And then Topping's conjecture was that actually it is not necessary that you assume that the energy is non-increasing to get the Struve solution. He said you can allow sufficiently small upward jumps in the singular time, and you still get the Struve solution. Just when you jump up too much, then you get the topping solution. And indeed, Rupfling could show that by an additional assumption, which is very natural, and this inequality here is really sharp, so you cannot improve that. So summarizing, we can say to obtain long-term solution, they introduced weak solution, and to not lose uniqueness, they said that the energy has to be decreasing, except in a finite number of singular points where the energy can jump up, but just to a certain amount of, up to a certain amount. And now we switch to the Ricci flow. So we are also interested when we introduce a weaker solution concept, maybe if we also can construct such a reverse bubbling singularity and to get another solution to the reference solution provided by Hamilton and Cho. So we just impose a uniform bound for the energy, but we do not say anything about the jumps of the energy. And we want to see if we get now another solution. So first, we need to define which kind of weak solution we would like to consider. So for simplicity, we can normalize again everything to unity. And we have seen this energy identity before. This was this uniform bound for classical solutions. And therefore, it is also natural to assume a uniform bound for our weak solution on the energy. So this is the first assumption. And the other is, since we wanted to describe the Ricci flow, we need also a time derivative. And so this time derivative should be in this Sobolev space here. And this means that this integral here is finite. And then we can introduce the admissible weak solution, so a function v in L infinity with respect to t and in h1 with respect to x. This here is actually the condition that the energy is uniformly bounded. Is called an admissible weak solution of the two-dimensional Ricci flow if there exists this weak time derivative satisfying this integral estimate, and if the function fulfills the Ricci flow equation in the weak sense, which is just given by this equality here. And then we have the following results. So we start with a smooth initial data U0. Then we know we have the reference solution provided by Hamilton and Cho. Furthermore, let V be the admissible weak solution for this initial data. But then we see at the end we get that U is equal to V almost everywhere. So therefore, we do not get a reverse bubbling singularity. So we have no reverse bubbling, so no different solution. So for the proof, in the first step, you need to show that also this admissible weak solution preserves the volume. And then in the second step, you take the difference of the reference solution and the admissible weak solution. This is called W. And you show it is non-negative on a short time interval times m. So here t is sufficiently small. And then with these two steps, you can show that W is equal to 0 almost everywhere on this time interval times m, but now t is arbitrary. And therefore, with this three steps, you can show that U is equal to V almost everywhere. So the step 3 is an easy argument. It's just by contradiction. So in the first step, we assume that t is sufficiently small, like in step 2. And then you assume by contradiction that W is not equal to 0. Therefore, we know by step 2 that there exists a set with positive measure such that W is strictly positive. Because in step 2 we showed it cannot be negative, so it must be positive. And then we immediately get with step 1 the contradiction, because here this is the volume with respect to the reference solution. This is the volume with respect to the admissible weak solution. We said that they start at the same time. It is volume preserving, so this is 0. The volume is the same. But from here to here, we just estimate this area by this smaller area U0, which is just a subset of it. It is the same, we just pull out e to the 2v. And this is strictly positive since this v here is strictly positive, so this is not 0. And so we get a contradiction, so this means that W is equal to 0 on a short time interval times m. And to get it for an arbitrarity, it is a standard argument. Just show that this set here is open, closed, and not empty. Open is clear, we can just start the flow at a later time. And closed is also clear because we have this Sobolev embedding. So we know that for one dimension, so we have that W is continuous with respect to t, and it is also not empty since we have 0 in this set. So part 3 is proved, and now let's check the time. You can also have a short look at the proof of step 2. Just an impression, it is a bit technical. First you need to write down the equation, of course, for W, which is given by this here. Then in the next step you show that also test function in the space L infinity H1 are allowed. And with the help of that, then you can replace all this V here by W minus, this is here. So first you show that these are allowed test functions. Then you can replace all phi by W minus. And now you start to just develop, let's say, all integrals. So the first integral now, you see that you can just express in terms of integral over m. This you can do by introducing this function f here, which is exactly the integrand we have seen before, and therefore the first integral is just an integral over m. And then going back, we see now we take now the second interval here. We can rewrite this in these two integrals here and then put everything together in the first equation. So then we arrive here. And the main thing is also that now we can replace all W we had before by W minus just by applying the definition of this W and gradient of W minus. And so now we arrive at an equation for W minus. And now it is just a technical estimate actually. You take every term, so this one you replace by these terms here, then you can absorb this integral on the left-hand side here. Therefore you arrive at this estimate here. And then you take the essential supremum on both sides to get this here. This is just technical. You will see at the end which estimate you want to have. So in the last step, we apply just Taylor to bound this from below by this term here for non-positive xi. So we can also estimate this function here from below, and then we arrive at this equality here, which is actually the main thing. So this is then smaller or equal than this here. A, B, and C as before. This is not so important which integral are they exactly. But then with technical estimates, you can estimate this thing here with the left-hand side. And so you see that the left-hand side is smaller or equal than an arbitrarily small constant times the left-hand side. And now you can choose this t so small that this factor here is smaller than 1. And then you see that this factor here, this function here must be equal to 0 on a short time interval. So just a last remark for the end. When you consider weak solution, actually you would also like to start with rough initial data, so initial data in a Sobolev space. And indeed, our result we have seen before is also true for initial data in H2. Then we just need another reference solution. And this is given by a result from Michael Struve. He showed when you start with initial data in H2, you also find an instantaneously smooth Ricci flow solution. And this solution also converges to a constant curvature metric. So we can just replace our smooth initial data now by a Sobolev initial data. So at the end, I just want to mention it is maybe a bit surprising that we not get this reverse bubbling singularity, although we start also with weak initial data. We immediately get this classical solution provided by Hamilton and Cho. But to be fair, we have to mention that in the case of the harmonic map flow, they started with H1 initial data, so it is rougher than we did because we started with H2 initial data. So and it is not really clear what happened if we start with H1 initial data. So, and at the end, muchas gracias por su atención.
So thank you very much, Franziska. Other questions?
Why you don't study higher dimensions?
For which case?
From the Ricci flow.
For the Ricci flow, yeah. For the Ricci flow, it is even hard to have this long-term solution because they do not. I think so far they do not have a really admissible definition for a weak solution concept to construct a long-term solution. I think Robert Hasselhofer did the first step in this direction, but I think in general they do not have this stuff. So I can do that, of course, but this is quite hard. No, I cannot. This is really hard to do this. So. Yeah, because of that, we focused on that case, also because of the similarity to the harmonic map flow.
And what about the prescribed curvature problem?
Yeah, there is also the possibility to consider higher dimensions, that is true, but then you change the curvature, of course, because Gauss curvature do you not have in higher dimensions, but you can consider, for instance, the Q curvature and so on. And there are also results from Luca Galimberti, and he did that for higher dimensions, yeah. And you can also do that, and think you get more or less similar results, but I'm not quite sure about that. Yeah.
Any other question? ¿En Toluca tienen alguna pregunta?
No los escuchamos.
¿Hay alguna pregunta en Toluca? ¿Por qué no los escuchan? ¿Nos escuchan en Toluca?
Ahí los vemos.
Los vemos, pero no los escuchamos. Alfredo, hablen más fuerte porque no los escuchamos. ¿Sí tienen preguntas ustedes? Bueno. Pues entonces, let's thank Franziska again.
Oh, thank you very much.